The universe is incredibly vast and mysterious. Its size has fascinated scientists, philosophers, and curious minds for centuries. While the spatial size of the entire universe is unknown, it is possible to measure the size of the observable universe, which is approximately 93 billion light-years in diameter today. But what does this number really mean? To put it in perspective, a light-year is a unit of distance used in astronomy and is equivalent to approximately 5.88 trillion miles or 9.46 trillion kilometers. This means that the observable universe is approximately 546.84 trillion miles or 878.58 trillion kilometers in diameter. This is a staggeringly large number that is difficult to comprehend. The answer to why the universe is so big lies in its origins. According to the Big Bang Theory, the universe was created approximately 13.8 billion years ago in an explosive event that caused its rapid expansion. Since then, it has continued to expand at an accelerated rate driven by mysterious forces such as dark energy. As the universe expanded, matter began to clump together under the influence of gravity, forming stars, galaxies, and eventually planets like our own planet Earth. Over time, these structures grew larger and more complex, giving rise to the incredible diversity of objects and phenomena we see in the universe today. The observable universe is just a tiny fraction of the entire universe, encompassing everything that exists. While the universe with a capital U includes all matter, energy, space, and time, the observable universe refers to the portion we can detect from Earth. This region is limited and extends to a distance of approximately 93 billion light-years in diameter. Light takes time to travel, so what we see in the observable universe are objects as they were in the past. Additionally, due to the expansion of the universe, distant objects are rapidly moving away from us, making them difficult to detect as their light is stretched and redshifted. The edge of the universe is a complex and fascinating enigma with no definitive answer. There are theories that suggest that the universe is infinite and has no discernible limit, based on the cosmological principle of isotropy. Another theory proposes that the universe is finite but curves around itself, without a defined edge. There is also the possibility that our universe is part of a larger multiverse, with other universes that may be connected or separate from ours. Furthermore, thanks to the James Webb Space Telescope, we have discovered the existence of the cosmic web, a large-scale structure made up of galaxies, filaments, and voids. This network reveals how matter is distributed and how galaxies evolve over time, arising from small fluctuations in the density of the early universe and amplified by gravity. Using the James Webb Space Telescope, astronomers have discovered filaments of the cosmic web in the early universe. These filaments were detected when observing 25 quasars, extremely bright galaxies with supermassive black holes at their centers, which existed shortly after the Big Bang. Among these quasars, a thread-like arrangement of 10 galaxies was found, anchored by a luminous quasar. These structures challenge our understanding of how the cosmic web forms and evolves, as they demonstrate that such filaments can exist early in the universe. Additionally, this discovery provides clues about how black holes may have influenced their environment at that time. The James Webb Space Telescope has made important discoveries studying the early universe and interstellar chemistry. It has identified the first strands of the cosmic web, revealing how galaxies and clusters form. In addition, it has detected for the first time the presence of a crucial molecule called methyl cation in a planet-forming disk around a young star in the Orion Nebula. This molecule plays an important role in interstellar organic chemistry, and its detection confirms its relevance in the formation of complex carbon-based molecules. The discovery also provides insights into how organic molecules can form and evolve in protoplanetary disks under the influence of ultraviolet radiation. These findings demonstrate the sensitivity and resolution of the James Webb and its ability to explore the mysteries of the universe and cosmic chemistry. James Webb has revealed that galaxies cleared away the opaque gas of the early universe, allowing light to spread freely. This event, known as the era of reionization, marked a key milestone in cosmic history. Using the James Webb, astronomers discovered that galaxies existing 900 million years after the Big Bang ionized the surrounding gas, causing it to become transparent. Bubbles of ionized gas around these galaxies grew and merged, gradually transforming the universe into its current transparent state. These early galaxies also exhibited surprising features, such as active star formation and unexpected structures, challenging our understanding of galactic evolution. By studying these ancient galaxies, James Webb has provided invaluable information about their characteristics, masses, and compositions, as well as their influence on their environment. These findings show how the James Webb reveals new aspects of the early universe that were previously hidden, allowing astronomers to deepen their understanding of the formation and evolution of galaxies. James Webb's Advanced Deep Extragalactic Survey (JADES) program is a leading initiative that uses imaging and infrared spectroscopy to study the evolution of galaxies in the early universe. JADES has made significant discoveries, including the identification of hundreds of galaxies that existed when the universe was very young. These galaxies, some of the oldest and most distant ever observed, provide key information about the formation of the first stars and galaxies. JADES takes advantage of the sensitivity and resolution of the James Webb and the infrared, allowing the detection of light from very distant objects that have shifted to the red due to the expansion of the universe. This approach has revealed galaxies at very high redshifts, demonstrating the power of James Webb to study the universe in its most primordial stages. The ancient galaxies seen by JADES are very different from the current ones. They are small, faint, and young, with massive stars in formation that emit ultraviolet light that ionizes the surrounding gas. These galaxies are crucial to understanding how the first stars and galaxies formed, how they reionized the universe, and how it evolved from its dark state to a transparent one. JADES reveals complex and diverse structures in these galaxies, showing stellar activity, supernova explosions, and mergers. It has also measured the size of nearby galaxies, showing us how they grow and change over time. With unprecedented sensitivity and resolution in the infrared, JADES opens new windows into the early universe and provides valuable legacy data for future research. James Webb studies galaxy formation by observing a protocluster of 7 galaxies that existed when the universe was young. These galaxies move at very high speeds within a halo of dark matter, which acts as a gravitational glue that holds them together. The James Webb used its NIRSPEC instrument to measure the velocities and confirm that they are united in a protocluster. Additionally, he used spectral data to model the future development of the protocluster up to the present day, predicting that it will grow and transform into the Coma cluster. This discovery demonstrates how galaxies clustered together early in the history of the universe and how they evolved into the massive structures we see today. It also highlights James Webb's ability to detect and study faint and distant galaxies in the infrared. James Webb studies the formation and evolution of galaxies by observing their shapes and structures at different cosmic moments. In early galaxies, he discovered complex, chaotic structures that underwent rapid growth and transformation driven by gravity and interaction with gas. In more mature galaxies, he revealed more regular shapes and structures, indicating growth and change over time. He also found even closer galaxies with morphological diversity, but similar to those in the nearby universe. These discoveries demonstrate the variability in galaxy formation at different times and how James Webb resolves details in distant galaxies, revealing their morphology and complexity. In addition, the James Webb has made it possible to study the chemical properties of distant galaxies, revealing information about the formation and evolution of complex carbon-based molecules. For example, he has detected a carbon molecule called methyl cation in a planetary forming disk around a young star, providing clues about interstellar organic chemistry and how molecules can form and evolve in cosmic environments. The James Webb has expanded our knowledge by detecting weak signals from distant and complex sources, validating its sensitivity and resolution in the infrared. These advances in the understanding of galaxies and cosmic chemistry are made possible by James Webb's unique ability to observe at infrared wavelengths and reveal hidden aspects of the early universe. The James Webb has revealed new details of the Pandora cluster, a complex and violent region of the universe located 3.5 billion light-years from Earth. The telescope has detected hundreds of distant galaxies in gravitational lenses in the cluster, amplifying their light and revealing their presence in the image. In addition, James Webb has studied the distribution and composition of gas and dust in the cluster, revealing information about the temperature, density, and metallicity of the hot plasma and cold dust. It has also observed the diversity and complexity of the galaxies in the cluster, showing a wide range of shapes, colors, sizes, masses, ages, and histories, as well as signs of star formation, supernova explosions, and mergers. These new details provide a more complete understanding of the evolution and interaction of galaxies in the Pandora cluster. December 25, 2021, and a new chapter begins for specialists. The hidden mysteries of the universe are revealed about half a year after the deployment of the James Webb Space Telescope. This advanced equipment has given us impressive images, but it has only been the preamble to an ambitious mission that will completely transform our understanding of the cosmos. In addition to investigating the first luminous structures and galaxies that emerged after the Big Bang, Webb's mission will also contribute to solving one of humanity's oldest questions: do we exist alone in the universe? To get to the bottom of this cosmic mystery, the 10 billion telescope will observe the atmospheres of exoplanets and verify the habitability of celestial bodies. In this sense, the mysterious signal recently detected is becoming a particular focus of discussion. But what are these current headlines talking about artificial signals in Proxima Centauri be really about? Is it really the sign of an advanced species, or can the reports be explained in another way? Proxima Centauri b is a question that is probably as old as humanity itself. Are we alone in the universe? Given the countless entities that shine down at us from the sky, is it possible that Earth is the only celestial body that harbors life? The problem is that, although researchers have managed to detect more than 5,100 exoplanets in almost 3,800 systems, we are still far from such a sensational discovery. We have not yet been able to prove the existence of extraterrestrial life. In fact, we know of no planet other than Earth that can be classified without a doubt as habitable. Often, the enormous distances that separate us from extrasolar worlds represent a substantial complication for a more precise analysis. However, things are a little different for our closest cosmic neighbor. No other exoplanet comes as close to our home as Proxima Centauri b. Although there are only 4.2 light-years between us and this celestial body, its presence was only detected in the summer of 2016 using the radial velocity method. The assumption quickly arose that experts had encountered a cosmic twin of Earth in the course of this discovery, and it is true that the exoplanet orbits its star, Proxima Centauri, within the habitable zone. As a reminder, in the world of astronomers, the habitable zone is the distance between a celestial body and its star in which water can exist in liquid form permanently. It is well known that the presence of liquid water is a fundamental prerequisite for the development of life similar to that on Earth. In the so-called Earth Similarity Index, Proxima Centauri b reaches a value of 0.827. As this official designation already reveals, this indicates how similar another celestial body is to our Earth. But does this mean that life is possible on Proxima Centauri b, or that it has already developed there? Well, according to our current state of knowledge, this question cannot be easily answered because we simply know very little about our extrasolar neighbor. The truth is that recent spectrographic analyses indicate that Proxima Centauri b has around 1.17 Earth masses. Furthermore, it can be concluded that the celestial body has a limited rotation, which means that it always rotates in the same direction towards its central star. This circumstance would mean that the exoplanet is divided into two zones that differ drastically from each other. Therefore, the day side, which is constantly illuminated, would be significantly hotter than the opposite, night side, which is in constant darkness. The planet's equilibrium temperature is estimated to be -38 degrees Celsius, but even this value is anything but set in stone. If the celestial body has a dense atmosphere, its surface temperature would be significantly higher due to the natural greenhouse effect. Furthermore, the report that Proxima Centauri b could host liquid water must be correctly classified. The orbital parameters and atmospheric composition that led to this exciting result in a simulation may not match reality. The mysterious signal, as just mentioned, Proxima Centauri b is probably divided into a hot, scorching day side and a cold, bone-chilling night side. However, this spatial division does not mean that the existence of life in the extrasolar world is categorically excluded. Between the two extreme zones there would be a narrow strip with temperatures that could pave the way for the development of life. Possibly, the hypothetical inhabitants, like us, managed to evolve over time from simple single-celled organisms to a highly developed species. If this is really the case, such a civilization would have had to leave traces on its homeworld, traces that we could also perceive from our point of view. In fact, in December 2020 a surprising discovery was announced that some experts interpret as an artificially generated radio signal. The source of the mysterious signal could be located in the realms of Proxima Centauri. Originally, researchers had set out to examine the host star for signs of flares with the help of the Parkes radio telescope in Australia. Experts wanted to find out what effects these radiation bursts have on surrounding planets. While evaluating data collected over a 26-hour period, James Webb, a SETI program intern, came across a conspicuous signal with a frequency of exactly 982.002 MHz. This finding has since been named BLC-1 for short. He has been considered an official candidate for an artificially generated radio signal from an extraterrestrial species. But that is not all. In the same period, other experts also found a striking feature in the Proxima Centauri system. They detected a bright, long-lived optical flare, which was accompanied by a series of intense and coherent radio bursts. However, the fact that BLC-1 is not currently elevated above the status of an interesting candidate is because scientists have not yet been able to classify the origin of the signal without a doubt. To prove that BLC-1 is, in fact, the technical signature of an extraterrestrial species, more observations are essential. But astronomers have not yet managed to detect the signal again, therefore another origin, such as a satellite or a natural source, cannot be ruled out. Suppose that life on Proxima Centauri has managed to flourish in the form of a technically advanced civilization. In this context, it would not be unreasonable for the inhabitants of the exoplanet to dedicate themselves over time to the task of illuminating the dark side of their home world with artificial lights. The fact that the discovery of a possible technosignature is currently associated with the future use of the James Webb Telescope is mainly due to the comments of Avi Loeb, an Israeli physicist who has been searching for new ways to discover the presence of new, previously invisible neighbors. In 2018, Loeb stated that the mysterious Oumuamua object could actually be the solar sail of an extraterrestrial species. Together with Amir Siraj of Stanford University, the Harvard professor published a study titled Detectability of Artificial Light in Proxima Centauri b. The scientists assumed that the hypothetical species on the exoplanet uses a similar type of light to our terrestrial LEDs. The result suggests that if the artificially illuminated night side reached 5% of the brightness of the day side, the James Webb Telescope could detect it with 85% probability. The more intense the artificial lighting, the greater the chances of it being detected from space. For example, if the nightside brightness stabilized at 9%, the detection probability would be 95%. It is important to note that a luminance of 5% may not seem like much to the naked eye, but compared to the artificial lighting on our planet, which is only 0.001% of the reflected light, the artificial lights on Proxima Centauri b would have to be 500 times brighter than terrestrial ones so that we recognize them as such. The study raises the possibility that the hypothetical inhabitants of the exoplanet use dazzlingly bright orbital mirrors to reflect the light of the host star on the night side of the celestial body. These mirrors could be seen by our telescopes. However, we must keep in mind that these ideas and thoughts published in the study are pure theory for now. It remains to be seen whether the experts' theses can have any basis in reality. If the James Webb Telescope were to detect any artificial light signature in Proxima Centauri b, it would be an exciting event and open up new possibilities for study.